Hi, everyone. Very happy to be here, excited to be here. So thanks for having me. So today I'm going to talk about Varonis journey, deploying RabbitMQ. So just a little bit introduction. So we are not the common use case at Varonis. We deploy RabbitMQ to our customers. And we deployed thousands of RabbitMQ instances to our customers, and sometimes in almost impossible environments. And we've managed to make it work fast and reliable, even though we don't use cluster. So we cannot use cluster. This is our concern. This is our constraint, excuse me. And this is because some of our clients, they don't have the resources to run cluster, and even though they don't have it, we should figure out. And we figured out how we can work without it and make RabbitMQ reliable and fast. So in the coming slide, I'm going to show you how we did this. Just a little bit about me. So my name is Ophir. I'm a software engineer at Varonis. This is my email. You can feel free to write me. A little bit about our company. So Varonis is a cybersecurity company. We protect our clients from insider threats. So most of the cases, when you think about a cyber attack, you think about somebody from the outside is trying to steal the data, right? Somebody from outside the organization is trying to infiltrate your organization, is trying to steal the data. But in insider threats, this is something else. This is somebody from within your organization. It might be an employee, it might be somebody else who has access to your organization. It can go and steal the data. And if you heard about people like, for example, Edward Snowden, right? This is an example of insider threat. So what we do, we protect our clients from insider threats, and we protect them from insider threats when somebody from within the organization is trying to either steal the data or sabotage the data. So this is a little bit of our company. You can feel free to go to varonis.com and read a little bit more about us. So, as I mentioned, we're not the common use case. So first of all, we don't have cluster. Again, we deploy RabbitMQ to our customers, and we don't use cluster. And I mentioned that, yeah. So we have this constraint, and sometimes the environment is too slow, and especially the network. So we already heard that in the previous session. I heard that other people in the industry also experience the same thing. So networks sometimes can be your enemy, and this is also the case. This is very common it's a very common case when the network is too slow and the bandwidth is too low, it's too small. Even though we manage to support high throughput using RabbitMQ, and in the next few slides, we're going to see that, and we're going to see what we do. Another thing is message loss. So we cannot afford losing messages. So in case there is an issue with the consumer, okay, or with the network, or any issue, we don't want to lose messages. And again, because we don't have cluster, we need to we need to think about how we support that case. And this is also something I'm going to talk about. Another thing is that we deploy RabbitMQ. Once we finish deploying RabbitMQ, we don't have access to it anymore. So our RabbitMQ should be self-managed. What do I mean by self-managed? Briefly, self-managed means that RabbitMQ should recover itself in case of an issue, and we should have an ability to monitor it. And we're going to discuss that as well. So, as I mentioned, we have quite a lot. So we have more than 7,000 customers, and we have tens of thousands of RabbitMQ instances running on our customer's machine. Just a few more words about me. So I'm a software engineer in the infrastructure group at Varonis, and we develop the infrastructure of a large scale distributed system. And I've been working with RabbitMQ for the last 4 years. I've been developing also custom plugins for RabbitMQ and multiple clients in different programming languages. And in the last 3 years, I've been also in RabbitMQ Summit. Really enjoy that, and I'm really happy that you are having me today. So goal number 1, supporting high throughput, right? If we have slow network. So in that case, what do we do? So our use case is this. Let's say we have 2 or more instances of RabbitMQ running on different machines, and we need to somehow communicate between those 2 machines. So we want to send messages from one instance of RabbitMQ to the second instance of RabbitMQ. And what we do, we use the common use case is using shovel, right? So you have a shovel that can consume messages from one instance of RabbitMQ, excuse me, and send it to the second one. But if you have a low bandwidth network, you might overload the network if you are producing too many messages, right? So in our case, we couldn't overload the network of our customers because we are not the only users of the network. So the customer had more services and more more services that are using the network. And when we first tried to work with RabbitMQ and to send messages over the customer's network, we figured out that we overload the network, and RabbitMQ just is overloaded with messages. So we had to figure out how we can increase the throughput and how we decrease the overload on the network when we send messages between 2 instances of RabbitMQ. So what we did, we built a custom plugin called Packing Exchange. And what Packing Exchange does is basically before we send, I'm going to show you the architecture of it in just in the next slide, but just briefly. So what it does, once the messages reach the queue that the shovel is consuming from, before that, they are being published to a custom exchange called Packing Exchange. And what the Packing Exchange does is pack the messages and compress them together, and then route the messages to the destination queue. And from the destination queue, the shovel is going to pick them and send them to the remote RabbitMQ. So the algorithm is very simple. We just take either 300 messages or 100 milliseconds. If 100 milliseconds passed, we compress all the messages and we publish them using the shovel to the remote RabbitMQ. And by using that method, we are using that method for all the messages that are being sent to the remote RabbitMQ instance. We don't use multiple shovels, right, for different messages. We use the same shovel for all the messages. Okay, so once the messages reach the remote RabbitMQ instance, the exchange is going to route the messages to the destination queue. By doing that, we decrease the network bandwidth. We decreased, our usage of the network by 10. Okay. So if, for example, before using that method, we consumed or we used our throughput was what 1 megabyte per second. We could decrease the 1 megabyte per second and increase the throughput, right? Use the same network bandwidth of 1 megabyte per second, but because we compressed it 10 times, we could use only 10% of the network. So that was a very important achievement. And again, it's very simple. We just built a Packing Exchange, and that looks like this. So we have here illustration. We have 2 machines. machine A and machine B, and we see that we are a distributed system. So we have microservices, right? And microservices are running on both machines, and they want to send messages to each other. So the microservices on machine A, if they want to send messages to machine B, they have to go through the packing exchange. Once they go through the packing exchange, the messages are compressed and sent over the network compressed. And this is how we decrease the load of the network and increase the throughput. And of course, once they reach machine B, they're going to go to the unpacking exchange. The unpacking exchange is going to unpack the message and decompress them and route them to the destination queue. Okay. So the second goal, which is very important, I'm going to talk about it a little bit more, is the resiliency to slow and stop consumers. So as we all know, RabbitMQ does give us the option to store messages, right? So you can, so you can use, you can publish persistent messages, and they will be stored in RabbitMQ. But there are some problems with that, and we're going to discuss this. So the main issue is how we handle bursts of messages when the consumer is too slow or the consumer is down. We need to figure out how we can handle such situations. Because, I mean, as I mentioned, we don't have access to RabbitMQ once we finish deploying a RabbitMQ to the customer. So let's say the consumer goes down and it's down for a week, right? And we produce a lot of messages. I mean, millions of messages, or let's say thousands of messages per second, right? But it can be a lot of messages, and it can be like teras of messages after a week, even more, right? And nobody thinks that you should store teras of messages in RabbitMQ. RabbitMQ is not a database, right? So we figure out that once the consumer goes down, we don't want to overload the queues, because there are problems with that. And what we've learned. So again, RabbitMQ is not a database. We don't want to store teras of messages in RabbitMQ queues. And we know that RabbitMQ was optimized to use memory to route messages faster, right? We want to use RabbitMQ as it was designed. It was designed as a fast router and not as a database. So the best practice is limiting the queue size, and limiting the queue size with a policy or with an argument on the queue, whatever you choose. But this is not enough, because if you limit the queue and you use, for example, publish rejects, right? You can tell the client, all right, the queue is full, stop publishing. You're going to overload the queue. I'm not a database, please stop. But what should the client do in that situation? So in that situation, the client has to decide where it's going to store the message. And it's a little bit problematic, right? Because the client cannot always have access to the storage, right? So if the client doesn't have access to the storage, there is nothing that basically the client can do about it. So it's better to tackle this issue from the server side, and this is what we did. So what we did on the server side in RabbitMQ, we extended it using a plugin, dedicated plugin. So once the queue reached its limit, okay, the plugin is going to store the messages in our storage system. So it can be on disk, it can be a database, it can be whatever you want. Okay, but it's not going to be inside RabbitMQ. You're not going to overload RabbitMQ. You're going to have full control of your data, of your persistent data, without using RabbitMQ as a database. So we called it storage exchange. Storage exchange was designed to store the messages, right, that cannot be consumed. And what it does, it monitors the queues that are bound to the storage exchange. And once the queue reaches certain limit, the storage exchange knows that it should not route this message further to this destination, and instead store the message on disk. Once the consumer is up and is fast enough to consume the message, the storage exchange is going to route the message back to the queue, so that the consumer can go back and consume the message. This way, we managed to make RabbitMQ more stable for the long run, and this way we also had control over our data, of our persistent data. So, as for example, if you go back to the issue with the network bandwidth. So let's say the network is too slow, or there is an issue with the network. So there is a disconnection right now between two instances of remote RabbitMQ. In that case, you don't want to lose the messages, right? Because our producers, our publishers, they're continuing to publish all the time, and they do that very, very fast. So I have to figure out what I do with all the messages. So I cannot just stop. I cannot tell the publisher just stop, and I cannot tell all the microservices in our system go and go and store the messages yourself. We need a server-side approach, and this is what the storage exchange does. We have here an illustration. So let's say we have a service that is publishing a message that is intended to both A and C. We have here two queues, A and C, and the green lines means that they are available. I mean, they are below the limit. And if I publish a message to both A and C, the message is going to be routed to both A and C as we normally would expect from RabbitMQ. And if we have messages stored on disk, the storage exchange is going to read the messages and route them as well. But let's say A is full because the consumer went down, or there is another issue, there is a bug in your system or something else. In that case, and I mean, we don't have access to the system. We cannot reboot anything. We cannot do anything because the publishing phase is, excuse me, is very, very, very high. So in that case, we want RabbitMQ to be self-managed. We want RabbitMQ to store the messages for us, but we don't want RabbitMQ to store them in RabbitMQ queue. And I'm going to explain why, by the way. I didn't explain why we shouldn't do that. I only told you that RabbitMQ is not a database, but I'm going to tell you explicitly why we think it's a bad idea to store tiers of messages in RabbitMQ. So in that case, the message that is intended to A and C is going to be written to the disk, and simultaneously the storage exchange is going to read other messages from the disk and route them to C because C is available. So all the messages to A are going to be written, and all the messages to C are going to be delivered. And it looks like this, basically. So we use multiple readers and one writer. So this illustration here, we have one writer, two readers, and let's say we go back to our illustration. Let's say A is full. In that case, the storage exchange is going to write the messages to the disk, and it's going to write them in chunks, okay, in fragments. And it's going to do that as long as there is no, as long as A is full, is above the limit or at the limit. So, and once A, and by the way, yeah, because the message is also intended to C, should arrive to both A and C. It should be routed to C, and C, the reader C is going to read from the disk, and this is this green line here, as you can see, the read line. So the read line in this situation here is the read line of, excuse me, this read line here, the green one is referring to QC because C can still read from the disk. And once the consumer of A is up and is fast enough, what is going to happen? So what's going to happen that reader A is going to read back its messages from the disk and receive all the messages. So this is how we make sure that our queues are staying below the limit, and they are staying small and not with a lot of messages. And instead, we are storing the messages where we want. So, yeah. So I talked about that RabbitMQ wasn't designed as a database, right? So, but what's the problem with storing a lot of messages in RabbitMQ? So first thing is the boot time. So the boot time might be an issue here, right? Because RabbitMQ will rebuild the indexes once you reboot it, once you restart it. Okay, so let's say one of our customers wants to restart RabbitMQ. Now, if we don't use the storage, right, storage exchange, and something was wrong, but the consumer, RabbitMQ will start for hours. So that's not a possibility to have RabbitMQ down for hours. If we use the storage exchange, RabbitMQ will start in a few seconds. So about resources. So if you compare it to normal queues also use a lot of memory, even if you publish persistent data. And this is because, as I said, RabbitMQ was optimized to use memory to fast route messages. So in comparison to normal queues, without the storage exchange, you are going to have a lot of memory usage. With the storage exchange, it's minimal. It's the same as with lazy queues. So lazy queue, it's an option. I know many now think to themselves like, why you don't use lazy queue? So lazy queue, that's an option, but doesn't give you all the abilities I just mentioned. For example, doesn't give you the option to store the persistent data wherever you want in SQL database, for example, or it doesn't give you the control over the data. And in addition to that, it doesn't solve the issue with the boot time. So lazy queues, it's an option, but not in our case. So what about publish reject? So as I mentioned, client-side approach, it's going to be slower, right? Because the client has to figure out what to do when it receives a reject from RabbitMQ, and now the client has to go and do some work, and go and store the message on disk, while the client could continue and produce more data and continue to publish or do something like that. So it's going to make your client slower. So that approach wasn't good for us. And as I said, client approach is not always possible if the client doesn't have access to the relevant storage. So RabbitMQ might be running on different machine, or might have access to the storage, but the client doesn't have it. So it's not always a possibility to do that. And it might also complicate your client, because you need to figure out how you share the storage between all the clients, between all the microservices. So it depends on your system architecture, but if you use microservices, it might be an issue. Okay. So yeah, I just talked about it. So we achieved that much faster boot time, so a few seconds versus a few hours. Improve reliability, of course, because RabbitMQ is less reliable when it holds teras of messages, because if you do that, you basically use it the wrong way. So, and again, more control over the persistent data. So, method number 2. So about method number 2, again, we are talking about publish reject, and we actually use that as well. So we have another custom plugin called Custom Exchange, which does basically the same thing as the storage exchange I mentioned, but instead of storing the message, it rejects the message. Okay, so the service knows that it shouldn't continue and publish to the queue. And why we did this, I mean, why we had to do it with the custom exchange? Why not just setting a policy on the queue? So The main reason is that so first of all, if you have unhacked messages in your consumer buffer, they're not counted. I mean, if your queue limit, if your queue just reached a certain limit, and the consumer of that queue has messages, these messages are going to be dropped. You're going to lose them because the limit of the queue doesn't count the unhacked messages. So this is how we solved it. So we basically what we do, we manage the queue limit from an exchange that monitors the queue that bounds to it. And this is how the exchange knows whether it should route the message to the queue or not, or reject the message. Another thing is that this way we implemented our own logic, because if you have a message that should be routed to several queues, but only one of them is just reached the limit, what RabbitMQ is going to do, it's going to reject the message, but might deliver, I mean, it will deliver the message to the queues that can have it. So in that case, if we have one queue that has reached the limit, we don't deliver it. We just reject the message, and we deliver it only if all the queues that the message should arrive to are available. So this is just our logic. Okay, last topic. I'm going to discuss this very briefly. I have 3 more minutes for questions. So last topic is guarding RabbitMQ. So RabbitMQ is not accessible to us once we finish deploying it, and we need to somehow figure out how we can monitor it. So I mean, the web UI is great, but I have no access to the web UI once I deploy it. So it's just like a closed machine of the customer. I cannot access it. So I need to make sure that RabbitMQ is self-managed, so RabbitMQ can recover from issues. And what do I mean by issues, and what do I mean by monitoring? So think about it like this. So let's say that you have your desired topology, like changes, queues, bindings, right? Something can go wrong. I mean, you might have a bug, for example. So it might be that an exchange and a queue, the binding just disappeared, right? In that case, you want your guardian, or let's call it how we called it, the Watchdog plugin. Our plugin just knows can detect that, and once it detects it, it can go and fix the issue. So if you know what is your topology, what your expected topology, it can fix it and also produce an alert. And it might be a security concern as well, right? If you have, like, let's say you have unknown users, for example, might be a security concern, right? Security concern. So if you have like a lot of queues, it might be also a security concern. Might be a bug as well, but it might doing damage to your system. Another thing is, as the RabbitMQ node, we monitor that the node is healthy. So we always check if the node is alive from the plugin. We also produce alerts when the queue reached a certain size. So we do our logic. We can decide, for example, what we do with the queue, what we do with the consumer, what we do with the messages. So this is how we implemented this feature with a dedicated plugin. And again, so excuse me. So Watchdog. So we call it a Watchdog plugin, but I mean, any plugin that you can build to monitor RabbitMQ, and in that situation, it's a good approach that can fix issues during runtime. So yeah, I think we have 10 minutes for questions, right? So I really hope you enjoyed the session, and feel free to contact me. This is my email, and I hope you enjoyed. I hope you got some good ideas so you can implement it in your projects as well. I know it was a little bit fast because we had only 30 minutes and we had to talk about it briefly. But again, if you are interested, feel free to contact me. And again, I hope you enjoyed.
Yeah, thank you for that. It was a very interesting talk, and I think the graphics was certainly some of the best I've seen today. Very imaginative. We do have some questions regarding the storage exchange. The first one that I saw was from David is the storage exchange public open? Is the storage exchange open public use?
Is the storage exchange is public? It's available to download.
I guess that's the question. Yes.
Yes. So right now it's not public. It's a proprietary plugin because it was built specifically for the needs of Varonis. So in order to make it public, we need to remove all the things that are dedicated specifically to Varonis. But we might do that. Yes. Right now it's no, but we might, of course, we just need to remove all the specific things to Varonis.
Okay. Well, another question is about the storage exchange again. I think most of these are. If you have both old messages stored on disk and new messages that are being published to the storage exchange, how do you make sure to deliver the messages in the order that they received?
Yes. So in that situation, this is what we do. I mean, it's not. This is not the solution to everyone that wants to apply such a solution. So what we do, if we already have messages stored on disk and we have new messages, because it's more important to us to deliver the new messages than reading the old messages, and it doesn't really matter to us the order they receive. We're going to first deliver the new messages and break the order just to make sure that the messages are make sure the new messages arrive to the queue. This is like an optimization because you want fast. You will get them. I mean, the consumer will get the messages faster if I deliver them without storing them on disk. So we break the order, but the other solution might be taking the new messages and write them to the disk and reading the old messages.
Okay, thank you. Another question about the storage exchange. Do you limit the amount of storage the storage exchange can use, and if so, how?
Yes, so we do limit it because, again, as I mentioned, we live in a system with other services, and we cannot overload the customer's storage. So we use a cyclical approach. Once we reach a limit, let's say your storage is 100 gigs, and you reached and the limit is 50 gigs. Once the free space is 50 gigs, this is the threshold. We start to delete old messages and write instead of them new messages. This is how we do that, and yeah. And of course, we delete also chunks of messages once all the consumers finished reading the messages.
Okay, thank you. And I have another question from Terence. I'll read it for him. With the storage exchange, are you using the storage exchange instead of persistent messages on durable queues, or in addition to?
So we use it in addition to, but you can use it both ways. You can use it. You can think about many approaches. It depends on how safe you want to be. So we use both. So we use both persistent messages and the storage exchange. But it's going to be, I think, in some situations, a little bit even better to use regular messages with the storage exchange as a nice combination. It's a nice combination between good performance and also high resiliency to slow or consumers that are down.